Hi everyone. So today we're going to start on the new section called complex numbers. Okay, so this is a pretty important section to go through. It's not too bad, it's just a few things that we need to get through. Okay, so we start with a simple problem of solving the following equation. So we have x squared minus 1 is equal to 0. Okay, so the way that we'd go about solving this is noticing that this left-hand side x squared minus 1 can be factored into two parts. So we have x plus 1, x minus 1 is equal to 0. And we know that this means that this first part is equal to 0, or the second part is equal to 0. So if the first part is equal to 0, we have x plus 1 is equal to 0, x equals minus 1. If we have the second part equaling 0, we have x minus 1 is equal to 0, or x is equal to 1. So this quadratic equation, degree 2, polynomial here, has two solutions. Okay, so this degree 2 polynomial has two solutions. Okay, one being x equals minus 1, the other being x equals 1. And you'll know that if you have a general quadratic, so something like ax squared plus bx plus c is equal to 0, then we can use the quadratic formula and we also get our two solutions. So we get x is equal to minus b plus or minus, so that's where the two solutions come from, the square root of b squared minus 4ac over 2a. Okay, and again, we get our two solutions. Now, we know from the high school work that we get real solutions when this discriminant is positive. Okay, so just a little note on that. When this discriminant, delta, which is b squared minus 4ac, when this is positive, we get two real solutions. Okay, and when the discriminant is equal to 0, we only get one solution, but we count it twice. Okay, so we say that it has a multiplicity of 2. Okay, so it may not be two unique solutions, but we still count the single one twice. Okay. Now, if this discriminant is less than 0, we say that we have non-real solutions. Okay, that's what we would have said back in high school. So if delta is less than 0, then there are no real solutions. Okay, so what do we mean when we say no real solutions? Okay, so when we say no real solutions, what we actually mean is that there are complex solutions. Okay, so what is this complex solutions or complex numbers? Okay, so to understand that, we look at another simple quadratic equation. So let's say we have x squared plus 1 is equal to 0. Okay, now we know it's a quadratic, so if we use the quadratic formula, we should be getting two solutions. Okay, so degree 2 polynomial gives us two solutions. However, here, if we try and solve this, we notice that the left-hand side can't be factored easily, so we're stuck with that. If we take the 1 across to the other side, we get x squared equals minus 1. X equals plus or minus root minus 1. But how do we make sense of that? How do we take the square root of a negative number? So just a little note on that. So before, we have been told that we can't take the root of a negative number. Okay, So that's what we know from before. We can't take the square roots of a negative number. That's one of the rules that we learned. However, we know that this is a quadratic. It's x squared plus 1 equals 0. So we really want this to actually have two solutions, not just no solution. Okay, so what we do is we invent a new number system. And the way we do that is by taking the square root of -1, and we say this is a new type of number. We call it R. So we invent a new type of number called a complex number. Okay, and we call it the imaginary unit. Okay, so this idea of imaginary is kind of like a contrast to real numbers. So we have real numbers, 1, 2, 3, and we have this imaginary unit, and together they form this set of complex numbers. Okay, so what is this imaginary unit? Well, we define it to be the square root of -1. So before we couldn't do that, but now we say, no, this is just a new type of number. We need to handle it. Okay, so it's going to be R is defined to be the square root of -1. Okay, that's the defining feature of this new type of number. So another way, or an equivalent way of defining this, is to say that this number squared is -1. Yeah, it's equivalent. So we can say I is the square root of -1, or we can define this number such that when we square it, we get -1. This allows us to find the two solutions of this previous equation. Okay, so how do we do that? Well, let's look at it again. X squared plus 1 is equal to 0. Okay, and now with this new imaginary unit R, we can factor this left-hand side. So in fact, we can factor it as x plus R, x minus R is equal to 0. So we can factor this using the imaginary unit. Now, let's just expand this out just to see that it works. So we're going to have x times x, that's going to give us x squared. X times minus r, so that's going to be minus r times x. Okay, we just treat it as a number. Then we're going to have r times x, so plus ix. And then we're going to have r times minus r. So we're going to have minus r squared is equal to 0. Now these two middle terms, minus ix plus ix, they're going to cancel. Okay, because one's a plus, one's a minus, they get cancelled. R squared is -1. So we're going to have minus 1, which is plus 1. Okay, so we get back to where we started. So in fact, this is a proper factorization of the left-hand side. So if we look at this, we're going to have two solutions from this. X plus r equals 0, so x equals minus r. Or x minus r equals 0, x equals r. So we see that we get the same solutions as before, the plus or minus root -1. But this root -1, we're going to call r. So we get these nice solutions, minus r and plus r. Okay, so this quadratic does have two solutions. The only issue is that they're not real solutions, they are complex solutions. So the equation x squared plus 1 equals 0 does have two solutions. as we expect, because it's a quadratic. It has degree 2, so we should have 2 solutions, but they're not real. So they are not real. Instead, they are complex. Okay. Right, so this is the first complex number that we meet, this imaginary unit r. In fact, we can use this to build up all of the complex numbers. So in general, a complex number, so typically we call it z. So z is typically used as the variable for complex numbers, and we're going to use this for the rest of the semester. So in general, a complex number z is given by z is equal to x plus ry. You might see that notation, or you might see z is equal to a plus rb. So sometimes it's given as x and y, sometimes it's given as a and b. It means exactly the same thing. Okay, so this x here, this is referred to as the real part of the complex number. So the real part of z. And this y, that is referred to as the imaginary part of z. Okay, so a complex number is made up of 2 parts. We have the real part, okay, that's the x or the a, depending on what you want to write. And we have the imaginary part, okay, which is the part that is attached to the r. Okay, so whichever bit is attached to the r, that is the imaginary part. So the way that we write this is we say that the imaginary part of z is equal to x. The real part of z is equal to x, and the imaginary part of z is equal to y. So we have these functions, real part and this other function, imaginary part, and they just extract whatever the real part and the imaginary part is. Okay. Now, this is a number, z is a number. So what we would like to do is invent some kind of arithmetic that we can use with these complex numbers. So with real numbers, we can add them, subtract them, multiply them, divide them. We would like to do the same thing with these complex numbers that we're inventing here. So first thing, how do we add complex numbers? So addition with complex numbers. Okay, so this is the first operation that we want to look at. So let's say we have a complex number z1, and that's given by x1 plus r times y1. And we have z2, which is going to be x2 plus r times y2. And we would like to define some kind of addition between these, much like we define addition between real numbers. So z1 plus z2 is going to be this first part, x1 plus I y1, plus the second complex number, x2 plus r y2. Okay, so this is going to be x1 plus x2, because we can add those two together, no problem. And then we're going to have r y1 plus r y2. But we can just factor out this r. So we get r y1 plus y2. And you see that the result is again a complex number. So this x1 plus x2, that's going to be the real part. And we have r times the imaginary part. So a complex number plus another complex number is again a complex number given by this expression on the right. Okay, what about subtraction? Okay, so again, we pick two general complex numbers. So we have Z1 is going to be X1 plus I Y1. Z2 is going to be X2 plus R Y2. And now we want to subtract them. We're going to do it very similar way to what we had before. Z1 minus Z2 is equal to X1 plus I Y1 minus X2 plus R Y2. And that's equal to X1 minus X2. And again, like we had before, this RY1 minus RY2, we can join those two together. And again, we can factor out the R. So we can have plus R, Y1 minus Y2. Okay, and let's highlight that again. So again, we have Z1 minus Z2, the difference of complex numbers is again a complex number where this first part, that's the real part. And this second part, that's the imaginary part. Okay, so addition and subtraction, quite easy. What about multiplication? Okay, so again, we're going to pick two complex numbers and we're going to try and multiply them to see what the rule is. So we have Z1, it's going to be X1 plus I Y1. Z2 is going to be X2 plus R Y2. We're going to multiply them. So that's going to be Z1 times Z2 is going to be X1 plus R Y1. X2 plus R Y2. And we're going to multiply this out. So the first bit is going to be X1 times X2, X1 times that. So we're going to have X1, X2 plus R, X1, Y1, just multiplying like that. And the second part, we can multiply that as well. We're going to have plus R, Y1, X2 plus R squared, Y1, Y2. Okay, R times R, that's going to be R squared. Okay, so again, we can write this in terms of a real part and an imaginary part to make it look like a general complex number again. So X1, X2, and R squared, that's going to be minus 1. So we have minus Y1, Y2 plus R, we factor that out, X1, Y1, and Y1, X2. And again, we see that this is a complex number with a real part given by this first bit and an imaginary part given by the second bit. Okay, so that's multiplication. What about division? Okay, so that's the last arithmetic operation, division. So we have again Z1 is going to be X1 plus I Y1. Z2 is going to be x2 plus r y2. And we want to find a way of dividing them to again produce another complex number. So we're going to have z1 divided by z2 is equal to x1 plus I y1 over x2 plus r y2. Okay, but this doesn't look like a complex number because what we want is this to be something like a plus rb. We're a bit stuck here with this division, but we incorporate a little trick just to make it look like what we want. We multiply by x2 minus ry2 over x2 minus ry2. So we're just multiplying by 1, but this is a special representation of 1. How do we get this? Well, we look over here at this denominator. We have x2 plus r times y2. So what we do is we replace the r with minus r. Replace r with minus r. We call this complex conjugation, and we're going to be looking at that with this fifth operation. Okay, but for now, we just think about it as plus r goes to minus r, and we multiply by this one factor here. Okay, so why do we do that? Well, let's multiply this out and see what we get. So in the numerator, we're going to get x1 plus r y1 multiplied by x2 minus r y2, all divided by x2 plus r y1, x2 y2 multiplied by x2 minus r y2. Okay, so let's multiply this out. So in the numerator, we're going to get x1, x2, okay, minus r x1, y2, plus r, okay, so plus r, y1, x2, and then we're going to have minus r squared, y1, y2. Okay, all divided by, let's multiply out the bottom. So we're going to have x2 times x2, so that's x2 squared, minus, I x2 y2 plus r x2 y2, and then we're going to have minus r squared y2 squared. Now these middle terms, they're going to cancel. So there and there. And the r squared is going to be minus 1. So we have minus 1. So that's going to be a plus. Same thing for the numerator. Minus r squared is going to be a plus. So in the top, we're going to get x1, x2 plus y1, y2 plus r y1, x2 minus x1, y2, all divided by x2 squared plus y2 squared. So this denominator is real now. There's no r term, so there's no imaginary part. Okay, so that means it's real. So what we can do is divide the real part at the top by the denominator. We divide the imaginary part at the top by the denominator, and we end up with x1, x2 plus y1, y2 over x2 squared plus y2 squared, and that's going to be our real part, plus r y1, x2 minus x1, y2, all over x2 squared plus y2 squared. And again, we've got this I here. So we have successfully written this complex number, z1 over z2. We want that to be a complex number. And we see that we've got this real part. And we've got this imaginary part. So again, it's a complex number. Okay, so division by complex numbers gives us, again, a complex number. Okay, so that's all of the basic arithmetic that we need. So we've got addition. Okay, so adding two complex numbers gives a complex number. We've got subtraction, multiplication, division, and I'm going to leave it for homework, exponentiation. So if we have some number z squared, you can work that out. Okay, but the next operation I want to go through, the fifth one, is called complex conjugation. Complex conjugation. Okay, so this works with a single complex number, okay, unlike the other ones where we need two complex numbers. So given z is equal to x plus ry, we write the complex conjugate of z as z star is equal to x minus ry. So this is what I was saying before. We replace r with minus r, and that gives us the complex conjugation of that complex number. So we replace r with minus r to get the complex conjugate. Okay, so sometimes you will see a star to represent complex conjugation. Other times you'll see a bar. So z star is the complex conjugate of z. Z bar is also the complex conjugate of z. Okay, it's just two different notations. They do the same thing. Okay, now just a bit of terminology with this complex numbers. Terminology. Okay, so again, given z equals x plus iy, okay, we say z is a complex number. So z is a complex number. Okay, we say that it belongs to the set C. So z is an element of C. Okay, much like we had x and so on being an element of real numbers, z is an element of the complex numbers. So that's this new set C. And we can write C as the set of all z equals x plus ry, where x and y are real numbers. Okay, so that's how we create the set of complex numbers. Okay, that's the first bit of terminology. Number two, we said this before, but x is called the real part. Okay, so x is the real part. Y is called the imaginary part. Okay. And number four, we say that the magnitude of z, okay, the magnitude of z is given by we use absolute value sign, Z. So it's like the magnitude of Z, the norm of Z, or the length of Z, something like that, but it's just a number, right? Okay, so it's not like a vector with components, but we'll see later on we can think of this as having components, but we have the magnitude of Z is equal to x squared plus y squared square root. Okay, so that's just a useful bit of terminology there. So when we refer to the magnitude of a complex number, we're referring to this real number here. Okay, and in fact, we can show that this magnitude of Z, we can calculate it like that with x and y. We can also calculate it without referring to x and y. We say that the magnitude of Z squared is equal to Z bar. So this right-hand side expression here, that doesn't mention x and y. Okay, so it just refers to Z, but it gives us the same thing. Okay, so this is another way of writing that down. If you don't want to write it in terms of x and y, you can write it as Z times Z bar. Okay, so last thing for today is the representation of complex numbers. So there are two representations that we're going to be looking at, the Cartesian form and the polar form. And the polar form is also called the Euler form. Okay, but we're going to get to that later. Okay, so first, the Cartesian representation of C. Okay, so why do we say it's the Cartesian representation? Well, if we go back here, so we've got a general complex number given by x plus ry. We've got two parts to it. We've got the real part x and the imaginary part y. Since there are two parts to this number, we sometimes say that complex numbers are two-dimensional because it takes two numbers to construct it, the x and the y. Now, x and y, that sounds like coordinates x and y. And in fact, we can write this as a coordinate type form. So we can have the following. We can have x along this axis, or we can say this is the real axis, because x is the real part. We can have the y-axis, or the imaginary axis, because that's the imaginary part. And then any points in this 2D space, so let's say this one here, any point is in fact a complex number, because we can look at this x part, we can look at this y part, and we can use that to construct z. So z is equal to x plus ry. So this isn't the Cartesian plane with coordinates. This is a two-dimensional plane of complex numbers. Okay, but you can see they are very, very similar, which is why we call it the Cartesian representation of complex numbers. Okay, so that's just a way of visualizing the complex numbers or the complex plane, as we will refer to it as. So this is called the complex plane. Okay, because it's like a 2D plane made up of complex numbers, hence complex plane. Okay, so that's everything for today. Tomorrow we will be going through examples of doing these different calculations. So adding, subtracting, dividing, finding complex conjugation, and so on. We're going to look at all of those examples tomorrow. Okay, if you have any questions about what we've gone through today, please just post a question on the WhatsApp group, or you can send me an email. Okay. And remember, the tutors are also available on the WhatsApp group. So if you have questions, you can ask them as well. Okay, I'll see you tomorrow.